Well, okay. I mean, what I will do, I've been sort of figuring on this all along, is to cut some of the details from the end down, and try to give you some idea as to some of the applications of electromagnetic theory as we have it. In fact, by the way, I looked through, it turns out that we have actually finished Griffiths as a text. We have one little bit of material left, and then we would have been done with Griffiths, but we haven't come to the end of Ohanian. However, Ohanian does actually, at the beginning of his text, say that this text is intended for 2-semester course. So if we don't actually finish Ohanian, it's okay. But I do want to make sure that you're exposed to a few more key ideas. So we really do have 3 more classes of new material today. All right. So today I want to talk about the fields from an oscillating source. Actually, let's think antennas. We've been through this, haven't we?
Yes. He says
This is America. It doesn't matter.
yeah.
Okay. An oscillating source and antennas as the example. But some of what I'm going to do is in an extreme limit where it really applies to emitting molecules and atoms. So an antenna typically is relatively large compared to the wavelength of the object of the electromagnetic wave that is emitted. It sometimes is. So I'll try to be clear about which set of approximations I'm using at which time. But basically, we can actually just write down an expression for the vector potential and then deduce the electric and magnetic fields, calculate the electric and magnetic fields from the vector potential. And last time around I wrote this and we did the justification. So the mu component of the vector potential at some observation point, 1 over c, current, I'll write it like this. It's at t prime, but I'm going to explicitly put it in. R minus r prime over c, comma, r prime. Charges moving around, or rather current occurring at charges and current, being present at positions r prime, and we integrate over where the charges are. And then the field's going to drop off as the distance, right? This is the way you could always do the calculation. If you know the currents as a function of time at every point in some space, you just go ahead and do the integral, and you're done. But we want to extract some meaning out of this rather than just putting up the integral. So we're going to look at this expression in some approximations, actually, and see whether we can sort of pull it apart, understand what contributes to what. Okay. As I said here, we have an oscillating source. That's not an extreme limitation, because basically I can always take any motion and break it down by finding its Fourier components. Right? So if I have an acceleration as a function of time, or a current as a function of time, I could just break it down into Fourier components. So what I'm going to do, as I did last time around, is deal predominantly with single frequency harmonically oscillating system, right? We're going to assume that charge looks like this times et minus omega t, that current can be written this way. Oops, I. And that all of the fields can be written in that form as well, right? That it's going to be a space-dependent part and something that oscillates. All right. So, I've already written this. This solution was the solution that we found we didn't find it, we stated it last time around with the assumption of the Lorentz gauge. We can find different forms for the vector potential depending upon the assumptions of gauge that we make. All of them have to satisfy, all the solutions have to satisfy the wave equation. And they are all equivalent, actually, it turns out, when we get into quantum mechanics and we solve for wave functions and Hamiltonians. The solutions are the same for those different gauges, but we've chosen the Lorentz gauge here. Yeah. Since I've explicitly now put the time dependence in T prime in here. And actually, I have to answer a question that I was asked at the last class with respect to, there was a third term in the set of partial derivatives that involved derivative with respect to T prime, I think it was. And I was asked, why is that term there? And the answer is that actually we have to write out the explicit dependence. That is, there's T and there's R, and we took our derivatives with respect to T and R. And T prime was not one of the variables of this, was not one of the terms that was held constant. So we actually, if we try to take a derivative with respect to T prime, we have to address the explicit dependence of T prime on T and R. So I hope that at least partially answers the question that was asked. All right, so I have got this dependence explicitly written into the currents, which basically says, if you want to know the field over here, you figure out what the currents were at that time over there, and then and you calculate the radiation from the currents due to that motion over there at that previous time. So you just put in this delay. T is equal to R minus R prime over C. This is complicated if the system has any size whatsoever, correct? If the system is, the distance that you are away from your distribution of current and charge is small compared to the size of the distribution of current and charge. So I've got some current loop here. Maybe it looks like that. I've got current flowing around. If I'm observing from this point here, then the distance to each one of these points in here is, the difference in distance is a significant fraction of the delay of the distance from here to there, from the center to there, okay? Then you have to do the whole interval. But if I go over here with respect to the size of the system, then the system's relatively small, and I can write the vector potential using some simplifications in the current. All right. So With this harmonic approximation for the current, the charge, and the fields, right? The vector potential is going to look like this. Let me see. I can write this for each of the terms. And I want to do this calculation in free space because I want to find the vector potential at a particular point. So I'm going to use these harmonic potentials to eliminate t as a direct variable in the calculation. If I do that, so I'm not going to do that, I'm just going to state that we use the harmonic approximation, or harmonic form, and I can make a substitution for t in terms of t prime if I wish, or r minus r prime. What is the time at which I'm making my measurement? And this leads to a of r 1 over c. Now,
Our absolute value signs?
where I've used k is equal to omega over c, right? So I got rid of my omega there. And yeah, so I've made a substitution for j. I'm using the 3 vector j, so I end up with a 3 vector a. And I have, oh yes, I can, yes. I have explicitly removed the time dependence because this is an oscillating field which just repeats, and the time delay can be included in the kr minus r prime. Okay, I've got a distance in here. So I could think of this thing as being frozen in space, but in time rather, but the wave oscillates and the position of the wave depends upon how far it has had to travel. Displacement of the wave, rather, will depend upon how far it has had to travel. And then from this,
Is that an R prime inside of J?
yes. Thank you. That's what I have in my notes, too. But it must be. B is just curl A. E is a little bit more complicated. We've used it before. And in this form, For the harmonic form, it looks like this, okay? So it's related to the magnetic field. All right, again, if we have a complicated current, first thing we do is break the current up into its harmonic components, and then we can calculate the field from each of these harmonic components, or the vector potential from each of the harmonic components, and then take curls and derivatives in order to find the fields. But again, this doesn't tell us a whole lot about how a system would behave and what dominates the fields that we actually observe. So now we want to simplify that. And we actually have 6 possible conditions, only one of which I'm going to pay attention to. Right? What have I got? I've got my system here of some size, all right? My length scales. So let's call this length, this size, that's the size of R prime. Is all in there, okay? And I'll just call that A for to make it easier for me to discuss it. Then I have the waves that are being emitted. All right, so that's lambda. All right. Then I have my observation distance. R minus R prime. So I've got 3 length scales that I want to be concerned with when I'm trying to figure out what that equation on the right-hand side means. Okay? And in terms of the wavelength and the size of the system, and the distance to observation, there are 3 conditions, right? One would be R much, much less than the wavelength. Let's call that just plain old R. No vectors, no anything, right? That is that the emission wavelength is really long, and I'm observing out there, but it would be easy for us to oscillate a system at a kilohertz, in which case or probably quite more reasonably 10 kilohertz, and then measure a meter away. And my little oscillator, might be a solenoid, which is this big, a centimeter. We're going to observe a meter away, so R is much, much greater than the size of the system. But if we're emitting at 10 kilohertz, then the wavelength's going to be hundreds of meters. I haven't figured it out. I'm sure somebody will calculate the wavelength for 10 kilohertz, right? Thousands of meters. So the wavelength can be much, much greater than R, and R much, much greater than A. But I'll stick for the moment to this situation. R of the order of the wavelength, and R much, much greater than the wavelength. This might correspond to an atom emitting light, for example. Right? The wavelength of the light would be several thousand times or million times smaller than the distance of observation. And then I have my conditions with respect to A and lambda, and A and R. All right? They're all going to be related to one another. But let's just say that A can be of order, it can't be smaller, so A of order R, that would mean that I just put my observation point inside the distribution, or just on the outside of the distribution. I can have A right, yeah, A much, much less than R, and having A much, much greater than R does not actually make sense. So I'll leave that one off there. So now I've done wavelength, yeah. And then I've got all the combinations of these, right? So, yes, I think we can have all the combinations. 6, yes, that's right. Good. All right, I'm going to confine myself to start off with the case where A is less than R, much, much less than R. So my observation point is well outside the distribution. And I'm not going to do that one. That one's hard. All right? Then I have these 3 cases that I can look at. And I'm not going to do that one. Actually, it's not that it's hard, it's just that there's not much to be learned from it in terms of the simplifications. So now I'm down to 2 cases, right? This one here corresponds to what we would call the static case. That is, that whatever happens at the observation point is just sort of following along with whatever is happening at the emission point. Right? So we can do all of the analysis as though the fields are static. There is still a relationship between the vector potential and the electric field and time dependence of the vector potential. Okay, but we can do the calculations in the way that we have done calculations before, and so I'm not going to do that. That brings us down to this pair. So that's what I'm going to talk about here. If then R is much, much greater than A, the size of the system, then when I make an observation, this is out at my R here, right, R prime there. This is my vector R prime. R prime is in there, okay? And I want to know, I know that distance to the center of the distribution, and then I need to know that distance. But that one's easy to approximate. I can say that R minus R prime is approximately equal to the distance from the average position here, the center, to there. So that's just the magnitude of R minus R prime dot R hat. So I've got a vector that goes from here to there, and I've got a vector that goes from there to there, and this is the correction that I would apply due to where I am in the distribution, okay? If this isn't true, you're going to have to do the integral. Skip the nears. Oh, yeah. I should give you, I give you the names, by the way. This one here is called the near zone. This one is called the far zone. And this one's called the intermediate zone.
Why zone and not field?
What?
Why zone and not field?
Because that's what the textbooks have chosen to use. I don't know. It's where you are. It's the field in the far zone. Oh, why is it not called the far field? I guess the solution is called the far field. Yeah. I expect, connect what I'm talking about now to Kirchhoff integrals for diffraction, in which case I will use the terminology of near field and far field. Okay. In the In this far zone, we can't ignore the exponential, all right? The differences in path length between this point and that point. Oh, sorry, yeah, in the far zone, right? Okay, between this point and that point may be substantial when measured in terms of the wavelengths, right? So I can't necessarily not toss out, but I can't approximate that as a constant, for example. 1. This one, yeah, maybe, okay? This term here, I look at it and I say, well, if the system is small, all right, compared to the distance of observation, I use that approximation over there, and I'm in the far zone, then, well, actually, lambda doesn't even come in here. I just have a distance here, and this distance change is relatively small. So in approximation, I'm just going to call that R, all right? But this one here, I can't ignore. So I've got that approximation. I'm going to put that into the integral over there, and A R is equal to e to the I k R over C R. I'll explain where terms come from. GB prime A of R prime e to the minus I k R dot R prime dot R hat. So that term there is just the R prime magnitude cosine of the angle. All right. If and because, because I'm in this limit here now, where, oops, no, I need one more thing. Much less than, yeah. There's one more set of approximations here. I'm combining these two, right? I can have, let's see, lambda greater than A, lambda of order A, and lambda less than A. The size of the system. I'm afraid I didn't mention those possibilities. So I could have 3 more. So it's 6 times 3. All right. Yeah, just because lambda is less than R and A is less than R doesn't mean I can't have those relationships between lambda and A.
And one more.
Right. So what I'm going to do to start off with is I'm going to say I'm going to work with the approximation where the wavelength is large compared to the size of the system. So let's call that case. I'm up to like case 6, I think, but I'm going to call that case 1 right now. Okay. If the wavelength is much less than A, then K R prime magnitude, magnitude R prime, this is going to be less than that, all right, is less than 1. And if that's the case, neglecting power, factors of 2 pi, it's got to be at least 2 pi smaller than the size of the system, than the wavelength, right? If that's the case, then I can expand the exponential. So I can write e to the minus I k R prime dot R hat is equal to sum n equals 0 to infinity minus I k R prime dot R hat to the n divided by n factorial. Just expressing the exponential in its expansion form as a sum. Why would we do that? Because it'll be useful to us to take a look at the current distribution or the charge distribution and ask whether it has a simple way for us to express it. And